Welcome back to this lecture on sequences and summations. In the previous segments we studied sequences, and now we're going to start manipulating them. So let's consider a sequence A sub p. What we're going to do now is to focus on adding up consecutive terms of that sequence. So for example, let's say we're looking at the sum A sub m plus A sub m plus 1 plus dot 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 all the way up to A sub n. Notice this is the sum of all the terms A sub I for I equals m all the way up to n. Now this is a very long expression to write, especially if m and n are far apart. So here is now a definition of a shortcut notation for this sum. We're going to write this sum sigma of A sub I. This is the uppercase Greek letter sigma, which we read as the sum. And A sub I is just the generic name of the sequence. Notice A sub I is basically already defined prior to computing the sum. What is not defined here is the value of I. Notice we have to specify that I starts at m and goes all the way up to n. And the way we do this in this notation is by putting I equals m below the sigma and the maximum value for I only at above the sigma. So here is the way you read this notation. It's the sum for I equals m up to n of A sub I. Again, just a shortcut notation for this long sum here. Now, often in textbooks or papers, you'll see an alternate notation which is essentially the same, except this component here and that one are written as subscripts and superscripts instead of being written above and below the sigma. Again, this is just a space-saving way that is used by printers. Yet a third way of writing this same sum is to do the sum of A sub I and then writing as a superscript of the sigma the fact that I is greater than or equal to m and less than or equal to n, both included. Notice the assumption here, of course, is that I is an integer because it's the part of the domain of a sequence. So make sure you're comfortable with the three notations. They are read the same way and they are written slightly differently depending on your preference. Now, let's define some terms to help us talk about this notation. In these expressions here, I is called the index of summation, since it allows you to go through all of the terms that are added in the sum. M is the lower limit of that summation, and n is the upper limit, as should be clear since m is the smallest index and n is the largest index of all the elements or terms in the sum. Since I is really just a dummy variable, it's basically like the name of the loop counter variable in a for loop. You can rename it anything you want as long as once you change its name, you substitute it everywhere where it's referenced inside the loop or here inside the sum expression. So you can call it I or j or k. Anything will do as long as it doesn't conflict with another name for a variable used inside that expression. Now, let's look at some examples of sums. Let's say the sequence A sub n is defined as follows. So what is the value of the sum for I equals 1 to 7 of A sub I? Well, it's going to be A sub 1 plus A sub 2 plus dot 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 plus A sub 7. And since A sub I is equal to I, this is really the sum of the first 7 positive integers from 1 to 7. So the final answer is 28. For a second example, let's consider the sequence S sub n equals 2 times n plus 1. In that case, what is the value of sum for I equals 0 to 5 of A sub I? Again, it's A sub 0 plus A sub 1 plus dot 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 plus A sub 5. So what is A sub 0? It's going to be 2 times 0 plus 1, or 1. A sub 1 is going to be 2 times 1 plus 1, which is 3. The next one will be 5. So we're adding the first 6 positive odd numbers from 1 all the way up to 11. And that sum adds up to 36. For our next example, let's consider S sub n to be defined as 2 times n minus 1 plus 1. What is the sum for I equals 1 to 6 of A sub I? Well, it's going to be A sub 1, which is 2 times 0 plus 1, which is going to be 1. A sub 2, which is going to be 2 times 1 plus 1, which is going to be 3. And notice what happens is you're going to get the same sequence as this one. And therefore, we're going to get the same sum for a total of 36. Now, this is interesting because what it shows you is that, notice we shifted the n by 1 downward here. We subtracted 1 from n. Otherwise, we have the same two generic terms here. And as a result, you get the same sum. We just had to shift the values of I up by 1. So we went from 0 to 1 and from 5 to 6. This is called index shifting. We'll talk about it again in a later segment. But for now, just be comfortable computing these sums, which is the learning objective of this segment. Now, let's consider another situation where we have more than one sums nested inside each other. So let's say we have two sequences, A sub I and B sub I, that are defined by the generic terms I and I minus 1 respectively. What we want to know is the value of this expression. Let's see how we read this. This is the sum for j is equal to 3 up to 5 of the sum for k equals 2 to 3 of the product A sub j times B sub k. So this should be, even if you've never seen that notation before, you should be familiar with the nesting of expressions like this. In fact, one way to think about how to compute this expression is to consider each sigma as a for loop and then just have nested for loop to represent this multiple notation. So we're going to go from left to right. Of course, this is the outer summation. So we start with this one. J is going to have to go from 3 to 5. So let's say we initialize a running total variable sum to 0, and then we have a for loop for j. Now for each value of j, what this is saying is we need to compute a sum over k. So we have a nested for loop here for k, goes from 2 to 3. And now for each value of j and k in the body of the inner loop, we just compute A sub j times B sub k, and we add that to the running total. So here is the algorithm, if you wish, you can think of going through while you're computing this, the value of this summation. So now we just have to do the math. This expression there is equal to A sub 3 times B sub 2. That's the first value of j and k. Notice for the first value of j, we have a second possible value of k, so we get A sub 3 times B sub 3, and so on and so forth, until we've reached the last value of j here, which is 5, and the last value for k, which is 3. Then, of course, we just have to plug in the values. Remember, A sub I is I, and B sub I is I minus 1. So here we're going to have 3 times 1, plus 3 times 2, plus 4 times 1, plus 4 times 2, plus 5 times 1, plus 5 times 2. Like so. And when you do the math, you end up with the value 36. So make sure you're comfortable with this concept of a multiple notation, which is very similar, if not identical, to these nested for loops that you are already familiar with. Now, to conclude this segment, let me briefly mention another variation on summations. Sometimes the elements or the terms you want to add are not part of a sequence. They are just based off of a set. So you could do a summation where S, which is the dummy variable in this case, runs over the element of a set. So what you're adding here is the value s squared, where s takes on any one of the values in the set 2, 4, 6. So what this is saying is you're summing the s squared, where s can take any one of these values. So this sum would be equal to 2 squared plus 4 squared plus 6 squared, which would be, of course, the sum 4 plus 16 plus 36, or 56. So there are several extensions like that of the summation notation. Remember, this is just a shortcut, okay, for a bigger expression. Notice if the set was much larger, then this expression will get really long. There's nothing fancy here, just convenient notations. Use it when you need it, and make sure you know how to understand and parse those expressions if you encounter them in this course or later.